Good morning and welcome to the AEE Canada East webinar with the topic of wastewater energy transfer systems. We're pretty excited for this topic. The wastewater energy transfer represents a pretty significant opportunity in many of the communities that we reside. So we're really kind of excited to bring this to you today.
Thanks, Andrew. I see people are still rolling in a bit. Pleased to have Noventa here, Cam from Noventa. Cam is a chemical engineer with over 11 years of experience in the energy industry. At Noventa, Cam is responsible for managing the wastewater energy transfer project currently being built at the Toronto Western Hospital, which has received a lot of press lately. So that's a pretty cool project for sure. He previously worked for Northwest Redwater Partnership in Alberta and was involved from the conceptual design through to commercial operation of the Sturgeon Refinery northeast of Edmonton. Cam's a licensed professional engineer in Alberta and Ontario, has a master's degree in chemical engineering from the University of Cambridge, and a bachelor's degree in chemical engineering from Queen's University. And today he's going to talk about some of their heat recovery technologies. As Andrew said, I think for this presentation, initially we were saying we probably hold questions for the end. I'm just throwing out the question to you, Cam. We have 9 people, so I don't know if the power outage affected attendance this week, because this is less than some of our typical presentations. So I don't know if it's more of an intimate talk today. So I don't know. We will probably have less questions, just less people, less questions. So I don't know if that changes anything for you, but maybe we can have more real time, more of a real time discussion because of that. Just thinking out loud, but it's up to you.
Yeah, no, I don't have any issue with that. So
okay, yeah, we'll see how the questions come in and how they are, and if it's only one every few minutes, then maybe it's easy to handle because it's a pretty intimate crowd today. So I'll let you go ahead. Thank you.
Perfect.
And maybe I'll just jump in one more time. We have this feature called Allow to Talk, and if we have an intimate environment and somebody wants to ask a question, I'm going to try and press the button and see what happens. So if you do have a question, if you do have a question, if you do have a question, put it into the Q&A. And what I'm going to do is I'm going to test out the promote to speak button and see how that works out. And we'll make this really intimate. Awesome. All right, Cam, it's all you.
All right. And does it switch over to my screen now? I think once. Just share it. Is Andrew Mark, is that popped up on your screen?
It has.
Perfect. All right. So if there are any, the slides aren't working, please just speak up and let me know. Otherwise, I'll just continue to roll on here. So thank you very much, Andrew and Mark, for inviting me to give a presentation today on wastewater energy transfer. And thanks, Mark, for the good introduction about myself. You saved me from talking about myself, which is always a good thing. So again, I work for Noventa, which is, I'll give a quick introduction in a couple slides what we do. And I'm here today to give a presentation on wastewater energy transfer. And this is more at a high level and how it works, how it integrates into HVAC systems and what the challenges are. So we'll get going. So just a quick summary of what I'm going to go through. So I'm going to give a quick executive summary of the presentation, briefly talk about who Noventa Energy is and what we do. Then I'm going to dive into wastewater energy transfer, explain how it works and how we can use wastewater to heat and cool buildings and do it more efficiently than most building systems currently have. Then I'm going to talk about the challenges associated with wastewater energy. So there's a couple unique challenges that we have to overcome. I'm going to talk about the Huber Thermwind system. So this is the system that Noventa, or the technology that Noventa uses to overcome the challenges, and I'll show how these pieces of equipment are designed to overcome the challenges. I'll give a quick overview of our project at Toronto Western Hospital and touch on a couple of different aspects of how this works in the real world and what we're learning there. And then at the end, just a very quick overview of Huber technology. And Huber is the company we're partnered with for the wastewater energy transfer equipment, and answer any questions. As Mark and Andrew said, We'll see how the questions roll in with the smaller group, and maybe we'll answer them during the presentation and at the end. So I'm open to either. So with that being said, just get into the executive summary. So why are we interested in wastewater energy transfer? Well, right now, as I'm sure everyone's aware, there is a large push in what I would say just to reduce the human impact on the environment. And there are a bunch of different terms and ways countries and people are doing it, whether it's net zero, whether it's reducing your greenhouse gas emissions, whether it's using less energy, becoming more energy efficient. It's to me, it's all driving towards the same thing, which is reducing our impact on the environment in a conscionable way. And one of the ways we can do that is through building HVAC systems, essentially. So buildings are one of the largest contributors to global warming, accounting for almost 30% of all CO2 emissions in North America. Noventa has partnered with Huber, which is a 187-year-old wastewater company, to bring an environmentally friendly solution to the market. And the solution that we use has many applications. It's called the Huber Thermwind system. So we can extract heat from sewers for heating and reject heat to sewers for cooling. We can do the same, extracting and rejecting heat just to the building's own sewage if the flow rate and the sewage, supply is large enough. We can extract energy from condensate and district steam buildings. And we also have some applications, this works well in some industrial applications where there are high percent dissolved solids, as we'll see when we're talking about the challenges that we overcome with the equipment. So really quickly, I'll just talk about who Noventa is before we dive into wastewater energy transfer. So Noventa Energy is a provider of proven, fully engineered technology alternatives for heating and cooling buildings. From wastewater energy transfer to thermal energy storage and energy sharing, we draw on our portfolio of exclusively licensed technologies and internally created IP to develop customized renewable energy solutions that reduce carbon emissions and manage energy costs for clients. So we are a very small company, but we like to, we pride ourselves on our competencies, identifying and conceptualizing what I would say are unique projects, developing energy master plans and the corresponding business cases, securing approvals, permitting, and stakeholder support. And that's an important one, as we'll see with the Toronto Western Hospital project later on. Detailed design and budgeting, contract negotiations, financing, project management, and operations. So sort of from cradle to grave in some respects to these projects. Our projects are typically subject to long-term agreements with creditworthy counterparties that will include provisions for accretive growth and continuous efficiency improvements to enhance value for the customer and our investors. So sorry for the corporate speak, but just a quick overview of who we are. And we work with a bunch of industry-leading partners. There, as you can see through the logos, quite a few well-known companies that we work fairly regularly with, and a bunch of them are working with us right now on our Toronto Western project. So I don't think I need to go into too much more detail here, and we'll get into wastewater energy transfer. So just from a very high level, what is the potential for wastewater energy transfer? So in North America alone, there are 168 billion liters of wastewater processed every day in the wastewater treatment facilities throughout Canada, the US, and Mexico. If we were to heat that water up or cool it down by just 1 degree Celsius, that would equate to about 350 billion kilowatt hours per day of energy, which is enough energy to supply the US for 1.5 months. So there is an incredible amount of energy, which we're basically flushing down the pipes. And as you see on the last point on the bottom here, over 90% of the heat used for domestic hot water goes down the drain. So the simple way to think about this is if you're having a shower or bath, or you're washing your dishes, anytime you're using hot water in your house, or even flushing the toilet because the water is still 20 degrees Celsius, you get the use of, you use the hot water for whatever you're using it for. But that water is still hot when it goes down the drain, and that's a lot of energy that doesn't have any further use. So what we're trying to do is tap into that energy and use energy that's already reuse energy, essentially, is what it is. So this is the global call it the global picture. The next few slides, I'm just going to talk about how we can integrate wastewater energy transfer into existing HVAC systems. So I'm going to go through, just give a brief overview of conventional HVAC cooling system. And then I'm going to go through what changes when we use wastewater energy transfer. And then we're going to look at the heating side as well. And this is just generic. So obviously there's lots of different solutions out there that people are using, but this is just an illustrative example. So in this example, we're assuming the building has a chiller or heat pump in the basement, and it's connected to a cooling tower to reject the heat to the atmosphere. In this situation, we have heat from the building is transported via a working fluid through a chiller and up to the cooling tower where it is rejected to the outside air. However, when we're cooling, we normally have hot, humid summer days, which impair the cooling tower performance because it's very humid outside and very, very hot. And as those things go up, the efficiency of the chiller is not the chiller, but the system as a whole is impacted. So on top of that, we obviously, our cooling tower operating costs, we have electricity. A big one is water. We have an open loop system with the atmosphere, and we're constantly losing water from this system to the atmosphere. We have to make it up. It's important to keep the chemistry of the system in the right range. And because we're losing water and ultimately some chemicals, there's lots of chemical dosage requirements to maintain the water chemistry. And then there's maintenance. So what happens with what we call the Noventa Huber cooling solution if we're using wastewater energy transfer? What changes? And later, or not later, but a couple slides further in the presentation, I'll go more into the details of these two pieces of equipment and how they work. But at a high level, we're still using the same chiller in the basement here, but instead of connecting it to a cooling tower, we're connecting it to a heat exchanger. And this heat exchanger exchanges energy with sewage. So we have what we call a wet well, which is tied into a sewer, and we pump sewage from the sewer to the other side of this heat exchanger to heat it up so the heat can be rejected from the building, and then it comes back to the sewer. We'll go into more details on that in a second. The important thing here is, again, the sewer is acting as the heat sink instead of the atmosphere. And normally sewer water is in the, let's say, 20 to 22 degrees, maybe it's 20 to 25 degree range, and it's water. So it's a significantly different heat sink source than the atmosphere that the cooling tower was using. And so in this scenario, we don't need the cooling tower. We have significant water savings. And the one thing, and sorry, I forgot to mention this on the previous slide, in a conventional HVAC system, our heat pump, I'm fairly sure everyone is familiar with coefficient of performance, but just in case you're not, if you measure the efficiency of a heating or a cooling system, we're generally talking about the heating or cooling energy produced divided by the energy input into the system. So for a conventional HVAC cooling system, we're typically looking at a coefficient of performance of between 4 to 4.5 or 400 to 450%. So when we switch to wastewater energy transfer, our COP almost doubles. We're looking at performing at a COP in the 7 to 8 range, which is significantly more efficient and less energy intensive. And so that's on the cooling side. So how does this work on the heating side? So on this side, we're looking at conventional, let's say, steam plant in a building. So we have natural gas is burned in boilers to make hot water or steam. The hot water is circulated to provide building heat. And even buildings with heat pumps usually require boilers to supply redundancy or peak demand. So in this case, we have CO2 emissions from the combustion going on. And our boiler efficiencies when combustion is usually 0.75 to 0.8, if we call that a COP. So it's very inefficient compared to even just the cooling we were talking about in the summer. So if we were to switch the heating to the wastewater energy transfer system, how would that look like? Well, the nice thing about it is we're using the same equipment we were using in the summer. We still have the heat pump. We still have the heat exchanger that we're exchanging energy with the sewer with. And we still have the sewer. And the sewer still can be the same temperature. That 20 to 25 degree range works both ways. All we're doing is switching whether we're tying into the evaporator loop or the condenser loop on the chiller or the heat pump, and providing low-grade hot water to the hospital HVAC system. So again, we're using carbon-free wastewater, replaces natural gas as the energy source to heat the building, and we use the heat pump to upgrade the temperature of the building hot water loop. And again, if we're talking about efficiencies, in our heating mode, our efficiencies, our COP, we're in the 3.5 to 4.5 range. So compared with the 0.75 to 0.8 of the steam plant, we have a large gain again in efficiency and reducing our energy intensity, which is important. So that was the overview of how we can tie a wastewater energy transfer system into a building. The next part, we're going to talk about the unique challenges that need to be overcome to make it work. As I always like to say, if it looks that easy, why isn't everyone doing it? And well, it's got some unique challenges. So we'll go through that.
Hey, Ken, quick question. Are you going to talk about like GPM flow rates required per ton, or would now be a good time to ask that question? I just want to make sure you're not already covering that.
Not specifically. Or is it related just like the sewer flow rate
Yeah, just curious, like, is there a rule of thumb you go by, like if someone's trying to do to understand if there's potential here for a small, whatever, it could be a small community or school campus or whatever, is there a certain flow of wastewater per ton of heating or cooling that you look at as a rule of thumb?
So the best example for that would, yes, there is. There's a minimum, not a minimum requirement, but as the flow gets lower, your efficiency or your ability to achieve the COPs that I was talking about decreases. So you're still able to do it, but just not, maybe instead of at this cooling COP of 7, you're at a cooling COP of 5. The best reference I have right off the top of my head would be for our Toronto Western Hospital project. We're using around 600 liters a second of sewage is the flow rate that everything's designed off of. And with that, in the summer, we're producing 2,400 tons of cooling. And in the winter, we're producing about 30,000 MVH of heating.
And is that sewage, is that wastewater being produced by the hospital or itself, or does it kind of just tie into the main wastewater system? And
the hospital is lucky in the sense that it has a large sewer. So it's the Mid-Toronto Interceptor sewer, which is a 10-foot diameter sewer that is one of the main feeder lines, I guess, in Toronto. And it is on the major street directly south of the hospital. So we're tying into that sewer and using it. There are a couple applications where we can look at tying into, let's say, self-generated sewage. But in general, you need to be looking, if you're looking to heat, say, a condo or a shopping mall or a hospital or any, say, decent-sized HVAC system, we usually try to look for a sewer with a good flow rate in the vicinity of the area.
Okay, thank you.
Perfect. Good question. So thank you.
There's one question, what's expected as a minimum flow? I guess that's one question.
Minimum flow in the sewer.
Yeah.
We're looking at it really depends on how much energy your system needs. so realistically, for the capital cost of tying into the sewer, you're probably, I'm going to want to say, looking at, I would expect to have let's say an economic case, 200 liters a second minimum, just to justify, unless it's a very shallow sewer that's close to the surface, in which case maybe you could go even lower. Or if you're tying, if you are able to self-generate the sewage and say capture it going out your building, then again that might drop the threshold there. And we're looking at projects like that as well. Any other questions there, Mark, or is that it for now?
That's it. Thank you.
Perfect. All right. Good questions. You're making me think on my feet and pull numbers together. So always good. So back to what are the challenges? So after we go through the challenges, I'll really show the nuts and bolts of how the wastewater energy transfer part of the system works. But one of the main things is if we're tying into the sewer, no matter what we do, we basically have to have a sewer, and that's shown as this red pipe coming into this bucket, let's say. We need to have a sump and be able to pump the sewage, because we need to be able to pump the sewage to the heat exchanger where we're doing the energy transfer. And as I'm sure everyone can imagine, pumping sewage is not a desirable service, both for maintenance and for selecting equipment. So and that's because large sewers tend to transport large pieces of debris, and they have a high TDS, or total dissolved solids. And so there's some nice pictures courtesy of Toronto Water here. Sump pumps, even if they're equipped with grinders, require costly maintenance and are subject to replacement every 3 to 5 years when pumping unscreened wastewater. So this is a big issue that is you need to put some thought into how to overcome. And again, I'll show how we've overcome this issue in a couple slides. So that's more on the screening side. If you're able to get the wastewater through the pump to the heat exchanger, we come up with 2 additional challenges. The first one is biofouling. And this is probably the greatest challenge for wastewater systems. Wastewater has a bunch of organic material in it. It's in the presence of oxygen. Lots of lovely things can grow in it. And you have very little control over that in a sewage system. So ultimately, the heat transfer surfaces in a heat exchanger are a great area for biofilms to start to grow. And they grow pretty quickly, as we'll see in a second. A 1 millimeter thick biofilm can reduce the effectiveness of your heat transfer by over 45%. Conventional heat exchangers, including wide gap plate frame heat exchangers, need to be chemically cleaned and disassembled frequently to restore performance. And as I'm sure everyone can imagine, it's not a very desirable job to be opening up and cleaning a heat exchanger that's in sewage service. And on top of that, you're exposing people to unsanitary conditions and odors and all of that. So it's not a good thing. So how quickly does this happen? So these are a couple charts just from a study that we found, which show basically show the effect of biofouling on thermal conductivity as a function of time. In this case, of time and velocity, and in this case, time and concentration. But really what we're seeing is it's fairly exponential growth. You have nothing, and then bam, all of a sudden you've lost you've had a significant impact on your ability to do heat transfer in the heat exchanger. And this usually happens very quickly. In these charts, we're showing 20 hours, maybe it's 2 days, regardless of how quickly it happens. In my previous industry, I was used to cleaning heat exchangers once every 4 years. So doing it a couple times a week is not, in sewage service, is not something that you want to be planning to do. Down here, we just show some pictures of a clean service, and then this is showing how the biofilm grows on the plates in a plate frame exchanger. So biofouling, as I mentioned, can occur as little as 20 hours and can reduce your heat transfer effectiveness by as much as 22% within the 20 hours. So this is a big issue that needs to be, or challenge that needs to be overcome. And then we also have the wastewater and sedimentary flows. So on top of the biofilm that can grow on your heat exchanger surface or heat transfer surface, we have to deal with the sediment and particulate that is in the wastewater flowing through the heat exchangers that's going to settle out in the nooks and crannies of your heat exchanger, which again is going to impact your heat transfer efficiency. So conventional heat exchangers, including wide gap plate frame heat exchangers, will need high pressure back flushes to dislodge all this particulate. And again, you can't always, you don't get back to 100% on a back flush. So you're again looking at costly maintenance on these heat exchangers. So those are the challenges. Now I'm going to talk about the system that Noventa uses. We partnered with Huber and we use the ThermWin system, which really consists of two pieces of equipment that are specifically designed to handle the challenges that I just described. And so I'm going to talk about how we do that. And there's hopefully some neat graphics that show it as well for everyone. So this is a busy slide. I apologize. The first thing to note here is that the numbers here do not correlate to the numbers on the graphic here. These are the numbers that correlate to the ones on the graphic. So I'm just going to explain on this slide in detail how the system works together with the pieces of equipment. And then on the next slide, I'm going to show some pictures and an animation on the heat exchanger. So this is the, we'll call it the generic setup for wastewater energy transfer. We have a sewer here, which is flowing under the ground. In order to tie into it, we construct what we call a wet well. And what that is it's an area where we can allow sewage to enter by gravity. So we typically tie into the sewer around the 4 to 5 o'clock mark and connect with a large pipe. That's obviously the size of the pipe matters depending on how much flow you need. But what we do is that pipe is connected to the Huber ROK4, and this is a screening device. So as we mentioned, the first challenge was the solids and pumping the solids and the impact on the sump pump. So what this screening device consists of, and I'll show pictures on the next slide, is it has a 5 millimeter perforated basket on the bottom. So all of the sewer water entering the wet well needs to flow through this 5 millimeter perforated screen before it gets to the pump, which obviously anything greater than 5 millimeters gets stuck in the screen. Now the beauty of this is that there is a large auger in the screen, and it lifts all of the large material that can't pass through the screen up this shaft. Sorry, go backwards. Up this shaft to the top, and then it's just discharged by gravity right back into the sewer. So we basically reject all of the solids that we don't want to deal with right off the bat. The water that makes it, or the wastewater that makes it through the screen is then able to be pumped through a sump pump, which we're depicting as this. I'm assuming everyone can see my mouse, hopefully. And that is pumped up to the Rowan heat exchanger. And this is the special heat exchanger we use that deals with the biofilm growth as well as the sediment still present in the wastewater. And here we either heat up or cool down the wastewater a couple of degrees, depending on whether we're heating or cooling the building. So whether it's winter or summer, I guess, what season it is. And then the water returns by gravity back to the wet well where it mixes with the solids coming up the top of the ROK4 and goes back to the sewer. So essentially all we're doing here is creating a little sewage circuit that we heat up or cool down a couple degrees and then send it straight back to the sewer. On the other side of the Rowan heat exchanger, as we talked about on the previous slides, we have a chiller or a heat pump connected. And depending on whether we're heating or cooling, we're either connected to the evaporator loop or the condenser loop to extract or reject heat to the sewer. So that's how the system works from, we'll say, a system overview. In terms of pictures, because pictures always do a lot more justice than words with respect to these things. So this is a picture of what Huber calls the ROK4. And so there's an auger going up the center of this chamber, as I discussed. It discharges the solids back down this chute. And you can see here, this is a picture of that perforated screen. You can, depending on the application, you can change the screen size, but they typically use a 5 millimeter perforated screen basket that self-cleans on the inside with the auger. So that's all designed so that you don't need to be going in there. The other item, as we talked about, is called the Rowan heat exchanger. And on the next, and so this is a picture of one unit here. It's typically, this unit here is about the size of a parking stall. I believe it's actually, this one's installed in Washington in a parking garage, Washington, DC. So on the next slide, we have a little animation that shows how the heat exchanger works. So I'll just get it going because it gives the Huber logo first. But this shows how we deal with the biofilm and sediment. So this is what I would call a modified shell and tube heat exchanger. We're going to see the inside of it in a second here. So on the shell side, we have wastewater coming in here, getting heated up or cooled down, and then flowing by gravity out the bottom. On the tube side, we have either the condenser or the evaporator loop of the heat pump or chiller connected to it. And over time, as I said, there's going to be biofilm growth and sediment deposit on the tube. So this heat exchanger, is a self-cleaning heat exchanger that has a mechanical trolley that scrapes the tubes as frequently as needed. Typically, it's once every day or two. The sediment from the tubes falls to the bottom where there's an additional auger. And that auger, there's a valve that you can't see here, obviously, that would open up only to discharge the sediment, and it self-cleans. And so because of this self-cleaning function, we're able to deal with the biofilm growth and solids accumulation. So just into more detail, this is a picture of the inside of a Rowan heat exchanger that's been in service. I believe this picture was taken about a year after it went into service. And you can see how effective the cleaning is. So I want to say fairly perfect heat transfer surface area here, but you can see all the biofilm growth and sure most people can imagine you're not going to get great heat transfer happening where the cleaning didn't go. So this is the technology that we've selected in how we deal with wastewater to address the wastewater energy transfer challenges. I'm now going to go into a quick case study on Toronto Western Hospital. And again, so this is a project that Noventa is currently doing. I'm managing from Noventa's side. So Toronto Western Hospital is an Ontario-based hospital. For those who know Toronto well, it's at the corner of Bathurst and Dundas. So it's just east of downtown Toronto, or sorry, just west of downtown Toronto. It's a very large hospital, over 1.5 million square feet. They currently have 120,000 MBH of boiler capacity and over 6,800 tons of chiller capacity. So what are we doing? Well, we're going to be ultimately providing about 90% of their annual heating and cooling demand using our wastewater energy transfer system, which equates to 9.5 megawatts of heating and 8.5 megawatts of cooling. And on top of that, we're converting the hospital's entire HVAC system, HVAC heating system from a steam system to a low temperature hot water system, while still maintaining, steam system redundancy. So why are we doing this, and why is the hospital interested? Well, we're saving them over a 30-year term an average of about $685,000 per year in operating costs. So that's your economic driver, which is a very big one. We're reducing their greenhouse gas emissions by about 8,400 tons a year. And because we're reducing or significantly reducing their cooling tower usage, we're saving over 45,000 meters cubed per year of water consumption. So lots of savings across a variety of fields that has us and the hospital interested in this project. One area I wanted to talk about was system integration. So one of the unique things I mentioned about this project is we're converting the hospital to low temperature hot water from a steam system. However, as we're only providing about 90% of their heating demand, we still need the ability for the steam system to supply heat. So what we've done, and this is just to call it a generic mechanical room schematic, but we have a hot water glycol coming to the mechanical room and going through the heating coil before it is returned back to our, call it the Noventa wastewater plant. If the temperature or the energy demanded by this exceeds what we're able to supply, in each of the mechanical rooms, we're able to divert the water, or the hot water being supplied through a steam, a heat exchanger that can heat it up further with steam. So essentially, the steam, this would happen on, say, very cold days during the winter, and the hospital system would basically see this as a warm winter day in terms of how they deal with it. So I thought I would share this with the group here. The other item I wanted to talk about was the wet well and sort of some other challenges that maybe people don't think of off the top of their heads. We talked about the technical challenges of dealing with wastewater, but as I'm sure everyone can imagine, actually doing a project of this scale, there's all sorts of other challenges that need to be overcome. So I focused on this slide just on the wet well, and this is a rendering of actually what we're going to be building on the south east corner of Bathurst and Dundas, right in front of the library. So this, just for size, is about 10 meters in diameter and about 40 meters deep. This is the sewer running along Dundas. It's about 40 meters underground there. You can see we have a very large connection to our wet well, and you can see these are the ROK4s and the screening devices and all the pipes that send the wastewater up to where we'll do the energy transfer. So this is obviously a very important part of wastewater energy transfer. You need to be able to tie into the sewer in some way. So before we even got our project off the ground, we had to approach the city and execute land use or encroachment agreements, as we're building this completely in the public right of way. So that was a important process to go through, and we sort of, at least with the city of Toronto, pioneered that one. We also had to come up or approach Toronto Water, the municipal water company, and figure out what the liability, what an agreement would be to allow them to allow us to tie into the sewer and deal with liability and all of that. So again, that was a fairly lengthy process to work through with Toronto Water and make sure that all of the concerns on both our side and their sides were addressed so that we could do this and successfully for both parties. And so there are a couple other agreements I won't go into, but these were the two big ones. And we got these out of the way before we started the project. Then you actually get the project approved. And this is a picture down here showing where the wet well is in plan view, along with all the other utilities that are already existing in the area. So we have to play in the sandbox that we've been allocated and figure out how to fit this thing without going through a hydro duct bank or a fiber optic cable or another a potable water line, etc. So there's a bunch of working in the public right of way and building this infrastructure has been a good learning experience so far, and it's been a fun challenge. But I thought I'd just highlight some other challenges with wastewater energy transfer that we're learning as we go. Really quickly, I think this is my last slide. Just talking on Huber Technology. So this is the company we've partnered with, and Noventa has the exclusive license to, I believe, sell and distribute the ROK4 screen and the Rowan heat exchanger. But Huber is a very old company, 187-year-old, 5 generations owned. So they've been around for a while. They're very successful, and they focus only on wastewater. So they know what they're doing in the wastewater area. They have over 45,000 products installed in 61 countries. They provide full engineering, design, and services supports for all of their products, and they're ISO 9001, 14001 certified. All of their manufacturing is done in Germany and Charlotte, North Carolina. So just a quick overview on Huber there. And that's the end of my presentation. So I thank everyone for taking the time to listen to me. And if I believe it's roundtable or questions, I'm happy to answer any question.
That's awesome, Cam. Thanks a lot. So there are a few questions, and I do want to try this allow to talk function. So if people will allow me to use you as a guinea pig, yep. I'd like to. I'm going to ask Jim Brown to ask his question. So Jim, I'm going to press the allow to talk button, and I don't know what's going to happen, but I've pressed it. So Jim, you look like you're muted, but I believe you can unmute.
Hello, can anybody hear me?
Oh, Jim, yep. We hear you. We hear you loud and clear. Why don't you ask your question to Cam?
Oh, I've lost audio.
We hear you. We hear you, Jim. Oh no, he's dropped his audio. So maybe we'll come back to Jim. I'm gonna press another button here. Hold on. This is exciting.
On the go.
Yeah, here we go. So Jonathan, I have pressed your button, so you could ask your question.
Hello.
We hear you, Jonathan.
Oh, great! I can still hear you too. Okay, I was just curious about the scrapers and how the scrapers work in the heat exchanger. Like you said that it cleans automatically. Is that just on like a timed interval, or is it? You said it's kind of as needed. Like what kind of sensors are in there to make sure that it's cleaning it when needed?
Yep. So I think I'm still sharing my screen. If I go backwards, and I think if I just generically go, you can see this, John, or I assume everyone can still see my screen.
You bet.
Yep. So what you're not seeing here is that on the we have a bunch of instrumentation that will be installed on both the shell and the tube side. So we'll have flow and temperature going in and out. So we'll be able to measure the performance of the heat exchanger and see how it degrades as a function of time. And so basically we're planning to just set a threshold where, you know, if the heat exchanger performance drops by 20 or 30%, that would initiate the cleaning cycle. We don't know whether we're going to, that's one option. You can also just do it as a, you know, it's something that happens at at midnight every night. And you do it during a time period where you know that there's low demand from the HVAC system, I guess is the way to say it. But it can be run as frequently as required, or as infrequently as required.
Okay. Can I ask one other question while I've got the unmute? Just curious about pumping stations. Do you guys ever work with integrating this kind of equipment into like sewage pumping stations where you already have like a reservoir to draw from? And maybe some of the challenges with that.
Yeah, no, we actually as I say, learning on the go, we have a very good relationship with Toronto Water. And this is really, the Toronto Western project is our first project doing this on the big scale. We've had lots of discussions with them, including visiting numerous of their wastewater treatment facilities. And there's we definitely are thinking about, and Toronto Water is open to the idea of, you know, tying in at, let's say, the wastewater treatment plant. I'd say we're more just waiting to figure out what the where the best opportunity to do that first is, or next, I guess is the way to say it. So yeah, in some ways that would make life very easy. And it could be as simple as, we are looking at applications where we literally just put this tube, like get rid of the wet well and just put this tube bundle into the wet well itself, if the application is right. So we can remove a couple pieces of equipment and pumping costs and just have the self-cleaning tube bundle submerged in somewhere in the wastewater treatment plant or another industrial, similar area in an industrial facility.
Right. Thanks.
No problem.
That's awesome. Jim, do you want to try again? Is your audio back?
It is back. At least it was before I clicked the button. The question that I had was, what does pumping maintenance schedule look like? Like, are the pumps easy to maintain, easy to access?
So are you talking about the wet well pumps?
Yes.
Yeah. So if I go back to the short answer is we are designing, this whole shaft is a class 1 div 1 area. So it's not on top of probably having a really nice smell in there. It's actually getting a person into the wet well is a lot of effort is required, I guess is the way to say it. We're trying to design out a lot of like we're trying brainstorming what we think the common failures will be and the common maintenance requirements will be, and we're trying to design those out, or design it so that we can deal with everything from the surface. So one of the things we're dealing, and you can't see it too well in this graphic, is we have a central chamber that the wastewater flows into here before it goes to these screens. And we know from Toronto Water that there's material like 2x4s, bicycles, and some other unique items that are fairly large and won't go through the screen that will probably make it into our system. So we're designing on top of the screens, we actually have an ability from the surface to raise a basket that would capture any of these large debris and just bring it straight out without having to enter the wet well. Now, if we need to do the sump pumps, which are these guys down here, we will need to enter the wet well, and we do have the isolation required to do so, and still keep some of it operational. But that's something we're looking at on let's say a 2-year time frame, and we don't want to be doing it once a month or anything like that.
Thank you.
Awesome. Awesome. I'm gonna unmute the next question asker. Here we go.
Hi, good morning. Thanks for the presentation. I just have a couple of questions, if you don't mind. What is the supply water temperature for heating, the maximum, and what is the minimum supply water temperature for cooling?
So are you talking on the sewer water?
I'm talking about the heat exchanger.
Yes.
Yeah.
Yeah, well, sorry, but you're talking about the.
I'm talking about the heating system. What's the temperature can be reached? You said low temperature heat, low temperature.
Oh yeah. So our hot water. So that on the hot water side, yes, we're supplying at 125 degree Fahrenheit and returning at 105 degree Fahrenheit. And on the cooling, we are. Oh, I'm working in Fahrenheit. I believe we're. I want to say 55 or 60 and returning at 40, I think.
Yeah, that's great.
Sorry, we're just supplying at 40 and returning at 55 or 60 for cooling.
Okay, so that's awesome. Just that now for the heating application, if you keep the steam as a backup, I think that you put in your example for the hospital.
Yes.
Which coil do you need to add? Do you need to retrofit new coils for heating?
Yes, we're putting all of the coil. We're pulling out all of the heating coils in most of the air handling units and putting in new heating coils that are specific for hot water.
And what's the typical number of rows in these coils, if you don't mind? Like ideally.
I don't have the I haven't I don't have the answer readily available, but they are a bit. I don't want to say double, but they're bigger than what was in there originally. So there was some engineering. We did a fair amount of engineering work to make sure that we're replacing them with the right coil.
Okay, thank you. And maybe just one more question, because you just talked about it, is the sump pump. I'm just, I just hope it's not a dumb question. On the sump pump, it seems that the static pressure is a bit high. Are you using centrifugal pumps, or you can use axial pumps?
These are, that's a good question. I want to say they are centrifugal pumps.
Okay.
But we haven't actually, we're still hemming and hawing over what we're actually purchasing there.
Yeah, because axial pumps tends to consume less power and transfer more volume. And I was confused because it seems that you're transferring large number of volumes and a high static pressure. So I wasn't sure which type is the best.
I'm pretty sure centrifugal, because we got at least 40 meters of head, which is large.
Yeah. Okay, that's good. I really appreciate it. Thank you very much.
No problem.
Cam, wouldn't the temperatures that you're able to produce depend somewhat on the heat pump technology as well? Like I think there are some industrial type heat pumps that even we provide that can go upwards of 160. They're dual stage. Dual stage heat pumps, they can go 160, 180 even. So I don't think it's limited to 125 necessarily, right?
No, we have some flex. That's call it the design number. We're using the heat pumps we're using are from Train, which I know is a competitor, Mark, but we're using a variety of different types. So I believe we have one agility, two Centrivacs, and two positive displacement ones, and they're set up in to be operated in series as well, so that we can optimize the supply temperatures to whatever we need. So we can go higher or lower depending on what makes the most sense, I guess is the way to say it.
Right. Yeah, I guess if you don't want to have to retrofit all your coils to work with low temperature hot water, I guess you could utilize the higher temperature water.
Mm-hmm.
Depends on the project, but yeah, okay. Thank you.
No worries.
Awesome. Awesome. I'm going to promote the next person to talk. Ty, you can ask your question.
Hi. So I'm working on a large development project. It's about 6 residential towers. And how would I determine viability on any project?
I
assume 6 makes sense, but if you were to, let's say, shrink that project.
If you want to, I want to say that the tricky part, oops, I don't know what I did there. The tricky part is figuring out what sewers are in your area and how much flow is going through them. We're very good at figuring that out. So if you're, if you want to fire an email after to myself or just Noventa, generic Noventa one, we can easily take a look at that location and tell you whether it's a good, whether you're in there's a good sewer nearby, and then from there you go from there. I guess.
Would you ever be able to tap off the sewage coming off of site itself?
Yes. We are looking at it's very few applications can be self-sufficient from their own generated sewage on site, but there are lots of applications where you can use it to supplement or offset your HVAC requirements as well, if it's not enough.
Okay, thank you.
Awesome. I'm going to promote the next question asker, Basil.
Hey, thanks. I have 1 minute of fame because I have another call that I need to be on in a minute. So what's the payback for the project? And then I have a follow-up question.
Yep. So this is based on a 30-year payback for Toronto Western Hospital.
And is there like a feasibility threshold in terms of maybe cooling capacity? I know that you mentioned the flow rates, but I'm probably looking at a more macro level. Is there like a feasibility threshold in terms of cooling or heating capacity, or?
Yeah, there. Like the way that we normally do things and I'll try to give a quick answer because I know you got to run. Is for Toronto Western Hospital in specific, they shared with us all of their existing operating data so that we were able to determine what their normal heating looks like, what their normal cooling looks like. And so we were able to develop an energy model that we use to tie it in with finding that optimum, what the optimum amount of heating and cooling for us to do is to make economic sense for both parties. Does that answer your question?
It does, yeah. Thank you so much. And again, I apologize. I'm in a rush. I have to disconnect.
Oh, it's a good question.
Was a great presentation and an excellent work.
Thank you.
Thank you. Have a good weekend.
You too.
That's awesome. So I actually have a question, Cam, while we're on this slide, and it's a great slide to be here because I thought of the question as you were speaking. I'm kind of curious, you're talking about, so when this was first proposed as a topic, in my mind, I was thinking what some of the other folks in the audience were thinking. Hey, we're going to tap into the sewer discharge from a site, right? So whether it be a hospital or whatever the case may be. So I was perhaps a little bit surprised to hear that you're tapping directly into the municipal sewer. Well, perhaps not super surprised, but it was surprising in that some of the points you have on the slide, the land use, encroachment agreements and the tie-in agreements, et cetera. So from your perspective, like what does the sales cycle look like for something like this? Are you knocking on doors? Are they knocking on yours? Or is it a little bit of A and a little bit of B?
Noventa is a small company and a new company. And so getting the first project, Noventa secured the Toronto Western Hospital well off the ground. And that's why they brought me in. So I came after the fact. That being said, with the publicity and the interest that the project has generated, we have a lot of interest, not only in the Toronto area, but I would say across the country and in other countries as well, even potentially in Europe right now, with people that want to do the similar things. So we have let's say Toronto hospitals are very interested in this and are watching this project very closely. But we have a lot of other interested in, there's a bunch of industrial customers that have wastewater treatment plants or applications with, let's say, dirty water with high dissolved solids, where we're looking at doing similar things. So it's very I don't want to say the sales engineers, but the team that does the feasibility studies is very busy, right? Has been very busy for the last year, which is good.
Yeah, for sure. I mean, it's a great answer. I mean, it's staggering when you present earlier on in your deck, when you present the opportunity available to us. It begs the question, why isn't this happening more frequently? But
I had the same, I remember when I was in university, I was asking the same question. There's all we just have to focus on using what I call it low grade heat and reusing it. And there's a huge potential out there, but it's the tricky part is always getting the business case to support doing the project. And from the Noventa perspective, like the Huber equipment that we're using, it's been around, like the Rowan heat exchanger, and it's gone through a couple iterations of design improvements, let's say, but it's been around and in service for, I believe, some of them now up to 15 years. And there's, I think there's close to 100 that are installed across a handful of countries. So again, what I'm trying to say is that the technology's been around for a while. It's just the project creativity to find the right application to use this and to get people interested in it is really been the challenge, I think.
Yeah, right on. Can you speak to the differences in permitting and attitude from municipality to municipality? Like, I know the project that you're talking about, or some of them are here.
Yeah.
They're in Toronto. You referenced a project that was installed with the same equipment in Washington D.C. So you're covering a bunch. Like, do you guys see consistency in the approach, or are you really needing to have a personality profiler come with you to every one of these engagements to figure out what button to press?
It's getting that, like, the slide I showed where I talked about the heat exchanger in Washington D.C. That was at the American Geophysicists Union Hall, I believe, and it was a project that was done that was before Noventa existed. So it was Huber directly with DC Water. We know the DC Water very well now, and I believe they were it was very helpful to talk with them while we were working with Toronto Water. What we're trying to leverage now, if we go outside of Toronto, is that now that we have let's call it a template of it's really the agreement we have with Toronto Water that is I want to say the tricky one. And as I'm sure everyone can imagine, municipal water companies are very conservative in their decision making for the right reasons. They are operating within very stringent permit or environmental compliance regulations, and the liability if something goes wrong as well as a big concern. So we want to use when we negotiated that with Toronto Water, the overall picture was we wanted to make sure that we could use it as a template if we needed to go to, I don't know, Calgary Water or whatever the municipality is. We want to, it's still obviously going to take some time because all of it has to be usually approved by the city council as well. But at least we have a starting point and can say that, this is what we're doing with Toronto Water, and we actually have a project that's up and running, and it's running well. So that's strategy there.
Yeah, that's awesome. Well, listen, thanks a lot for coming out today and answering the questions, and thanks to everybody who played guinea pig with us as we tried this new promote to speak function. I really liked it. I think it made for a more robust round table, and we're going to try and do it more frequently. Thanks again, Cam, for spending the time with us this morning. It was a great presentation, and certainly there's, you say you're busy, and I suspect that you and others will be even more so going on to the future. You're right. Low grade heat is an opportunity that is, for the most part, untapped. So hopefully the tap opens for you. Thanks for your time.
Thanks very much for having me. I enjoyed presenting. So yeah.
Very good. Thanks, everyone. Have a wonderful day.